So welcome to everybody. Today we have Camillo Brena from Scuola Normale Superiore, who will talk about weakly non-collapsed RCD spaces, which are strongly non-collapsed.
Okay, thank you very much. Thank you for the introduction. Thank you also, of course, for the invitation. The talk of today is based on a work written with Nicola Gigli, Shoei Honda, and Shiniu Tsu. Okay, so this is the plan of the talk of today. The first part is a brief introduction, which contains bits of preliminaries, but also the definition of RCD condition and the application to Riemannian manifold. So this will be something important to understand the second part, that is the one about the definition of non-collapsed space, the main result of the paper, and also a couple of applications. Last, I give a sketchy proof of the main result of the paper, passing through some intermediate results that should be of some interest in themselves. So let me start with the first part. Okay, so if one wants to do some calculus, a good starting point is the definition of Sobolev space. So there are several possible approaches. I'm gonna talk a few minutes about the one borrowed from by Chigger. Okay, so take a metric measure space, so that is a set X, a complete and separable distance B, and a Borel measure, which is assumed to be finite on balls. And now, if one wants to go towards the definition of Sobolev space, a starting point is the definition of the Chigger energy, a possible starting point. So one takes the relaxation of this functional, which is the 1/2 of the integral of the square of the local Lipschitz constant. And the local Lipschitz constant is defined in this way, more or less. So recall that if you are in the smooth setting, this is the modulus of the gradient. So in other words, taking an L2 function, its Chigger energy is the infimum of the limit of these values. When you have to take this infimum among all sequences of Lipschitz function converging in L2 to F. So once you have this, you define the Sobolev space as the domain of finiteness of the Chigger energy. And the important result, this is an old result, is that taking a Sobolev function, there exists an L2 function that I denote in this way, so as the modulus of the gradient of F, providing this representation. So starting from an energy, so a real value, one builds almost everywhere defined object that plays the role of the modulus of the gradient, which is suitable to have this representation. That is something rather classical. Okay, I have to say that it is possible to define the object gradient of F by looking to normed modules introduced by Gigli, but there is not enough time today, so I'm just defining the modulus of the gradient of F. So this is just an L2 function for today. Okay, so one may prove that this is fully coherent with the usual approach. Okay, so if you want to do a bit of more calculus, so going towards maybe a notion of second order calculus, a first starting point is to ask some other assumption of the space. So one is of infinitesimal Hilbertianity introduced by Gigli, and it amounts to ask that the Chigger energy is quadratic. And this is the definition of a possible definition of infinitesimal Hilbertian space. So if this Chigger energy is quadratic, you can define this object for a couple of Sobolev functions. Again, I'm not telling you what are these gradients, even though I think you know already, but just what is this coupling. And this is defined by polarization. So again, if you go to the Euclidean or smooth context, you know what it is, and this is simply the dot product defined by polarization. Okay, so once you have this stuff, you can have a notion of Laplacian. So taken a Sobolev function, it may happen that there exists an L2 function that here is denoted by Laplacian of f, satisfying the usual formula of integration by parts for every Sobolev function G. And of course, as you are testing the Laplacian against many Sobolev functions, and these are dense in L2, you have that the Laplacian, if exists, is unique. So, okay, this was just some calculus on quite general spaces. And now let me introduce the RCD condition. So, taking a couple of numbers, k and n, you say that a metric measure space is RCD star kn. Here, I will discuss a bit in a moment about this star. If the following 4 conditions are satisfied, that I'm going to show you. So the first is technical, is a control, a bound on the growth of the measure of balls, but you can forget about this. The second one is the Sobolev to Lipschitz. So if you have a Sobolev function whose gradient is uniformly bounded, then it must be almost everywhere equal to a Lipschitz function of the right Lipschitz constant. And this already in the smooth setting asks for something of the space to the space. So for example, the space must be connected more or less starting from this. So it's something quite important. Third, the space is infinitesimally Hilbertian. And as I told you, this is just to start doing some calculus on the space. And so if you have this, you can do some calculus that looks like the usual one. And you can ask for the last condition that is probably the most important. And this is the one where k and n appear. And it's the weak form of the Bochner inequality. Here I mean weak form because this object usually does not have a Laplacian as defined in the previous slide, but the Laplacian is a measure. So instead of defining this measure Laplacian, to see this inequality, just take a positive test function phi, multiply both sides, integrate, and then integrate by parts, so that you drop this Laplacian to phi and you have no problems. Okay, so here we have the n that is present here, and k here, and usually one says that k is the synthetic bound from below for the curvature of the space, for the Ricci curvature, whereas n is a synthetic bound from above for the dimension of the space. And so you see here k, and then they appear in the last condition. And maybe in a minute it will be clear why this k and n have this meaning. Okay, just to be precise, I will call this RCD condition, dropping the star in the rest of the talk. If the RCD condition has a slightly different meaning, but if the measure is finite, is m is finite, then these two conditions are proved to be equivalent. If m is not finite, there is not, as far as I know, a reference that proves equality between those two conditions, even though I think everybody believes that they are equal. So here I'm doing an abuse, but probably in a few years it will turn out that this is correct. This is indeed correct. So now, the last part of the introduction, I want to deal with the Romanian manifolds. But first, let me fix a couple of things and some notation. So take a smooth Romanian manifold. You can define this metric Laplacian, right? That is the trace of the Hessian. This is just a purely metric concept. That is the usual definition. And also, one can see the metric Laplacian in this way as a scalar product. So let me tell you a few words about this. So at every point, you have the Riemannian metric, which is a bilinear form on the product of the fibers of the tangent space. And so as this is bilinear, you see it as a linear form, as a linear function on this, acting on this tensor product going to R. And so it's an element of the dual of this module, but the dual then go component-wise. So G, you can see G, the Riemannian metric, as a section of the tensor product of the cotangent bundle with itself. But also the Hessian lives here, And this is a scalar product thanks to the metric, so it makes sense to take this scalar product. So in other words, if you want, read everything in coordinates. This is the trace of a matrix, and this is the scalar product between two matrices, meaning in the entry-wise sense, so take every corresponding entries and take their products. And this is the one that induces the Hilbert-Schmidt norm. Then, okay, so we have this Laplacian, but it may happen also that you have a measure on the manifold, and that the resulting space is infinitesimal Hilbertian. And so, as in the previous slide, you have another notion of Laplacian, that is the one defined by integration by parts. So a priori, these two objects are different, and indeed, usually they are different. And how they are related is a key part of the proof of the main result and of the understanding of a non-collapsed space. So I will talk about their relation in a minute, but let me say that when I write here the G down, it's because it's the metric Laplacian defined in this way, and if there is not the G, then it's the one defined by integration by parts. Okay, so this is first example for the RCD condition. So take a Riemannian manifold, say complete and without boundary, connected, endow it with the volume measure, and the volume measure is the Hausdorff measure of the right dimension, right? So dimension equal to the dimension of the manifold. And here I recall the well-known Bochner identity. So it allows you to compute the metric Laplacian of this quantity in terms of this, and this is the Hilbert-Schmidt norm of the Hessian, and here appears the Ricci tensor. Okay, so now you have this. That is the very definition of the metric Laplacian, and it's the trace of a matrix, more or less. So if you use Holder's inequality, you obtain this fairly easily. It's a direct computation. And here it appears the dimension of the manifold. But also, on unweighted Riemannian manifold, the metric Laplacian is okay to integrate by parts. So you can drop the G here, this one and this one. And then, if you have a bound from below for the Ricci curvature, you can bound this by the bound you have. Bound this by this equation, and what you obtain is the Bochner inequality. So the space is RCD Kn, with K the bound from below for the Ricci, and N the dimension of the manifold. If you have an RCD Kn manifold of this kind, you choose wisely F, and you go the other way around. So this is an equivalence. Okay, so just to understand non-collapsed spaces, I have to add a little freedom, so a slight complication. And that is the case of a weighted manifold. So again, this is the Bochner, but a couple of considerations are needed now. So the first is this, is the relation of the Laplacian that is good to integrate by parts and the metric one. And so this is called the Witten Laplacian in this case. And you see that here we have a correction term that depends on the function defining the weight. And also, one needs the definition of modified Ricci tensor, where this n is actually usually bigger than this n. And so, if you are willing to give up the control on the dimension, you can modify your Ricci tensor adding the Hessian of the function defining the weight and this negative quadratic form. This negative quadratic form goes against any bound on this tensor, but here, if you increase this big N, this becomes small. Otherwise, in the other case, you just either keep the original Ricci tensor, or you have something that is not suitable to have any bound from below. So, with this in mind, if you plug this and this equality into here, and you do the computations, you obtain this. So this is an equality, but here there are some positive terms that I do not write. This computation is not so difficult, but it has to be done with care. You can find it in Villani's textbook, for example. Okay, so assume you have a bound from below for this modified Ricci tensor, so you can bound from below this. discard this positive term, and what you obtain is the Buckner inequality. And so you have that the space is RCD Kn. But now K is the bound for the most modified Ricci tensor, and N is usually not the same N, given the dimension of the manifold. As before, choose wisely the functions. You can prove the other way around, the other implication. Okay, so just to wrap up, what is important in this slide is that if you add a weight and you are RCD, then it means that you have a bound from below for the Ricci tensor. It means that either you are in this case or in this case. So if you give up on something on the dimension, then it's fine. If you don't want, then the weight must be constant. And it means that the manifold, it's not weighted in reality, because the weight is something like a constant. And this will be the concept of non-collapsed that I'm going to introduce in this part. Okay, first, just a little bit of history of this concept. So the concept of non-collapsed spaces was introduced by Chiger and Kolding in their series of papers about Ricci limits. And so, if you take a Ricci limit, that means a pointed Gromov-Hausdorff limit of this sequence, and this is a sequence of Riemannian manifolds, all of the same dimension n, and satisfying a uniform bound from below for the Ricci tensor, then this is what is called a Ricci limit. It may happen that the measure of the unit balls are uniformly bounded from below, and in this case, they said that the convergence is non-collapsed. And this definition was motivated by better regularity properties enjoyed by this metric space under this assumption. For example, if this is the case, the Hausdorff measure of the dimension equal to the dimension of the manifolds is a random measure. And so this was the part by Chiger and Kolding, but this definition works only for Ricci limits. In the no-smooth framework, in the RCD framework, we do not have usually such sequences at our disposal. And so another definition that is intrinsic has to be given. And this is the one given by the Philippis Gigli. So a metric measure space is a non-collapsed RCD Kn space if the reference measure is the Hausdorff measure of the right exponent. The right exponent means that the exponent you want to put here is the same bounding the dimension. Relaxing a bit, the definition of weakly non-collapsed, so means that instead of asking equality, you ask for absolute continuity. Just a remark, whenever the reference measure is an Hausdorff measure of some exponent on an RCD space, this is an integer, so it's a natural number. Okay, so one trivially sees that the non-collapsed spaces are weakly non-collapsed, and the question that usually comes to your mind is that, is there any converse of this implication? What happens? And so this is the main theorem of the work. And so that it states that these two conditions are morally equivalent. So that if you take a weakly non-collapsed RCD Kn space, then you can multiply the measure by a constant, so a real number, and you obtain that the space is non-collapsed. So, in other words, a weakly non-collapsed space has a reference measure which is a constant times the Hausdorff measure. Okay, here we have to renormalize, right? Because in the definition of non-collapsed is required that the reference measure is precisely Hn and not up to a multiplication by a constant. Okay, so this is maybe this is exactly the result of the paper. But first, let me motivate a bit the study of non-collapsed spaces. And okay, their interest started with Chiger and Kolding, and they proved several nice properties of non-collapsed spaces, which have then been generalized in the no-smooth setting, in the RCD setting. by the Philippis, Gillis, and other authors. But I don't want to speak about these classical results, but I want to recall a couple of facts and a couple of lines of research. And the first is the notion of parallel transport that has been developed for non-collapsed RCD spaces, not for general ones, only for non-collapsed. And similar consideration for the isoperimetric problem, where the author studied the isoperimetric problem on non-collapsed RCD spaces. So up to now, these two, so the existence of parallel transport and characterization of isoperimetric problem are available only in the setting of non-collapsed RCD spaces. It's possible that they can be extended, and maybe somebody will do in the future, but up to now, this should motivate just a bit the study of non-collapsed spaces, because also in the recent literature, they turns out that they are used. Okay, so last part about the history. About the history of the proof of the main result. This result has been already proved by other authors, but asking additional conditions. So besides the RCD condition, if one asks a bound from above for the sectional curvature, Kapovic and Ketterer were able to prove the result. Same, but with another condition. So Hahn proved this theorem for spaces, for regular spaces in which the metric space is a Riemannian manifold, but you can choose your favorite measure on it. And last, Honda proved the result for compact RCD spaces. I have to say that the paper followed Honda's key ideas, and the difference between the two papers is in the presentation and mostly technical. Today, I'm not talking about technical details, so if you know this paper, it may seem that this seminar is more or less also about this paper by Honda. I will just maybe outline the difference in a following slide, but this is what I wanted to say about this. So now, let me go through a couple of examples and applications. The first is that Breu Semola proved that if you take an RCD space, then there exists a natural number called the essential dimension of the space, bounded by the synthetic bound for the dimension, such that the reference measure and the Hausdorff measure are mutually absolutely continuous. Here, this restriction is just technical, so just think about these measures to be absolutely continuous. So, in other words, take an RCD space, its reference measure is a weighted Hausdorff measure, with a weight that can be very irregular, but it's a weighted Hausdorff measure of the dimension given by the essential dimension. And okay, so if you inspect the definitions, you have this other definition of weakly non-collapsed space. So a space is weakly non-collapsed if and only if the essential dimension is n. And this is usually maybe the easiest characterization of being non-collapsed, weakly non-collapsed, but also it's something that explains us what is happening. So as in the slide for Riemannian manifolds, you have this n that is a synthetic bound for the dimension, and you have this n that is a geometric dimension, right? So asking that is non-collapsed means that the geometric bound coincides with the functional analytic bound on the dimension, so that there is no gap actually between these two values of n. Okay, so with this in mind, let me go to the next slide. So take an RCD space and define this density as the limit of this ratio. And the existence of this limit follows by Bishop-Gromov volume growth inequality. But just if k is equal to 0, this ratio is decreasing in R. So this limit has to exist. And a corollary of our result is the following, is that these two are equivalent. So if the set of points on which the density is finite has positive measure, so in other words, if the set of the points on which density is finite is not too small, and if and only if, right, then the density is finite at every point of the space. And this gives me the occasion to introduce this. And this was the definition that Ita Beppus proposed for non-collapsed space. So previously, this was known to be an intermediate result between being non-collapsed and weakly non-collapsed, but after the main result of this paper, you see that this is actually equivalent to the other definitions. Okay, the proof of this is straightforward. So from right to left, it's trivial, right? From left to right, it goes as follows. So as you have this by the properties of the essential dimension and differentiation of measures, this means that the essential dimension must be n, so maximum. So the space is weakly non-collapsed, and hence if you renormalize the measure is non-collapsed, so the density is uniformly bounded, but at almost every point with respect to Hn. But this density is lower semi-continuous as a consequence of Bishop-Gromov again, and so this bound extends to the whole space, and you update this. Okay, so this was the conclusion of the second part. Let me go to the last part, the proof of the main result. Okay, here one needs a lot of preliminaries because one needs a good knowledge of modules, of algebraic operation with modules, for example, the tensor product, normed modules, I mean the one introduced by Gilli, but also a calculus of the second order on RCD spaces. There is not enough time to introduce all this knowledge, but you can pretend to be in the Riemannian setting. So if one just thinks about the usual objects, you will get the key takeaways. But of course, the technical, I will skip the technical part, so it will not make much difference between knowing what are the objects or thinking about the usual ones. Okay, so let me go to the proof of the main result. And to prove the main result, we use the key result, and the key result is maybe more important than the main result, but let me show you what it is. So take an RCD space and let lowercase n denote the essential dimension. This may be different from this, so nothing has to do with being non-collapsed up to now. Take an open set, say bounded and connected, satisfying this technical bound. So it is a uniform bound from below for this ratio, uniform both in X and in R. And okay, so under this technical assumption, we have the equivalence between these two assertions. The first is that if you take functions supported in the set, which are regular enough, the Laplacian, that is defined the integration by parts, and the trace of the Hessian, that is the metric Laplacian, coincide. And the second is that the reference measure and the Hausdorff measure of the essential dimension are one a constant multiple of the other on the set U. So just to convince you that this makes sense, go back for a minute to the Riemannian setting, to the weighted Riemannian setting. And so if the reference measure is e to the minus v times the Hausdorff measure, the second holds if and only if this is constant. So if and only if this is always 0. So if and only if we have this equality. So if and only if Witten and metric Laplacian coincide. So this is something that in the Riemannian setting is easier, but at least it tells us that it makes sense. Okay, so this is how one derives the main result starting from the key result. So take a weakly non-collapsed RCD space So in particular, as I said before, the essential dimension is maximal, so it's n. Take an open-bounded connected set. So think U to be a ball. This will be enough for what we have to do. So U is a ball. Recall that we had this technical assumption, and in this case, this is automatically satisfied. And the reason is, again, Bishop-Gromov. So say for a minute that k is equal to 0. This is decreasing in R. So if you want to bound it from below, just take R equal to 1. And then it turns out that you have to bound a continuous function on a ball. But balls are relatively compact, so the bound from below must be non-trivial. And also, we had the equivalence between two conditions, and one, it was this one, that the Laplacian is the trace of the Hessian, and this follows by a result by Hahn. So let me recall, this was the key result, technical assumption that is verified, this assumption that is verified by Hahn, so this must hold, and so the reference measure must be a constant multiple of the Hausdorff measure on the ball. But the space is connected, so this extends to all the space. So we prove that the space is actually up to multiply by 1 divided by C, the space is non-collapsed. Okay, so now let me say a couple of things about the proof of the key result. As I told you before, the strategy of this proof is borrowed from Honda's paper, but Honda could do simple computations as you was in the compact case, and so he could use the expansion of the ith kernel by eigenfunctions, and computations really simplify a lot. In this case, in the general case, the difficulty is technical, but we overcome this difficulty just via approximation arguments. And these approximation arguments heavily use the Gaussian estimate for the ith kernel. Now, I do not want you to read these estimates, but what is important in what I want to say is that, see, we can estimate the ith kernel, its gradient and its Laplacian, so estimates from the 0 to the second order, by something that decays exponentially in the distance between x and y. And so if x and y are far from the diagonal, this is small. And it means that whenever you have a ith kernel, you can assume that everything happens in a bounded subset, because what is outside this bounded subset is more or less 0. And so you go back to the compact case. Still, we do not use this expansion, eigenfunction, but anyway, going to the compact case allows you to use some more powerful arguments. Okay, so this is maybe the main difference between the two papers, but now let me explain a bit the strategy. So the strategy is the following: is to replace the original metric G by a smoothing metric GT. And so you take the ith kernel PT and consider this map that maps a point to a function, and the function is the ith kernel with a variable prism. Okay, so what is done here is to pull back the smooth metric pull back the flat metric of L2 to the RCD space X. But in other words, as maybe this definition of pullback can be rather obscure, you can say that GT is defined in this way. So the smoothing metric is a superposition of this tensor product of differentials. And here you can give your favorite meaning to the integral, maybe in a weak sense. What we did is to use a Buchner integral. Okay, so once you have this smoothing metric GT, you want to play a bit with it. And this is maybe the burden of the proof, is this technical computation. And it's the computation of the adjoint of the covariant derivative of the metric. I will just say what it is here, but let me say something about this. So you want to compute this stuff, and the result is this. So it's the differential of the Laplacian of a function which is the ith kernel computed on the diagonal. Here it's interesting to see that this t becomes a 2t here. Okay, so just to see how this is used, this was the computation. So you want to compute this integral. The first step is to integrate by parts, so use the very definition of the divergence. And it turns out that you have the differential applied to this vector field. Now, by this equality, by this computation, you write it in this way. And this is the very definition of the adjoint of the covariant derivative. So this goes to the other side, becoming a covariant derivative. Now simply use the calculus rules for the covariant derivative, and it turns out that you have this. So in the end, you have that this is equal to this, and it's what I recall here. This is the result of the previous slide. Okay, so now what one wants to do is to see what happens when t goes to 0. And indeed, there are some convergence statements. So as t goes to 0, if you renormalize objects with the right renormalizing factor, that is this one, so t to the n plus 2 divided by 2, you have that this term goes to 0. So this is what is here. And the metric gt goes to the metric g, but a Radon-Nikodym factor appears here, so a Radon-Nikodym derivative. And we are happy that this happens, because this is what we want to estimate in the end. We want to prove that it is constant in the end. So now, why does this happen on U? And the fact is that similar convergence statements hold for all the space, but if you want to have this normalization instead of another one that is more complicated and not suitable here, you have to use the technical bound that we had. So the technical bound that was in the assumption of the lemma allows us to use this normalization factor. Okay, now I'm not telling you which kind of convergence we can prove here, but we will use the convergence just in a weak form here, so in a very mild formulation. So it's no surprise that any kind of convergence here it will work, what I'm doing now. And so what I'm doing now is to assume that AJS supporting U, so everything here happens in the set U, multiply both sides by this normalization, and let t go to 0. What's at the left-hand side goes to 0, and this is for here, and what's at the right-hand side goes to the same, but without the t, and with the presence of this Radon-Nikodym derivative. And so this is the result after the limiting procedure. Okay, this is what Honda called the metric integration by parts. And the reason is that if you simplify these differentials, then you obtain this formula. And this formula is an integration by parts as the one for the Laplacian. But instead of having the reference measure, you have the Hausdorff measure. It is purely a metric concept. And instead of the Laplacian, you have the trace of the Hessian. So now the proof is almost finished once you have this metric integration by parts. So let me do my last two slides about the equivalence of the two assertions of the key lemma. So this is one. I recall here for you the metric integration by parts. And so the one assumed that the Laplacian is the trace of the Hessian. So under this assumption, plug this equality into here. So you obtain this. And then what one does is to consider this left-hand side and do a formal computation. Now it's formal here because I'm not justifying any irregularity, but this can be handled with an approximation argument. So this computation can be made rigorous. So take this, integrate by parts formally, and then use the Leibniz rule. But now this term was this one. So if you plug this into here, you see that this term is equal to this right-hand side. This term and these are equal, so they disappear. And so this is the only factor surviving. And so you have that this is equal to 0. But you're testing these gradients against lots of functions, f and h. So by density, this gradient must be 0, and which in turn imply that this radon-Nikodym density has to be constant. Okay, so this was the proof of one implication of the key result. And now let me say a couple of things about the other direction. So 2 implies 1, that it is actually way simpler. So again, this is the formula of metric integration by parts. Assume that the reference measure is a constant multiple of the Hausdorff measure. So these two radon-Nikodym derivatives cancel, and hence you have this, but this is exactly the definition of Laplacian, right? Here, because this is the definition via integration by parts of the Laplacian. So the trace of the action must be the Laplacian by the very definition, and uniqueness of the Laplacian, as we seen before. Okay, so this concluded also the proof of the key result, and so thank you very much.
Okay, thank you, Camillo, for your beautiful talk. Are there any questions?
Yes, I have a question. I want to ask if this this argument with that you use for this equivalence can also be used to deduce something also in the collapsed case. For example, that the Laplacian is the trace of the action plus so it's like the Witten Laplacian, where the gradient of the weight essentially appears. Of course, there is the problem of the regularity of the weight.
Yeah.
So it's a sense the similar to the identity that you wrote formally. I think in 2 slides ago there was the gradient.
Okay. Yes, it was.
No. The second to last slide. Yeah, this one here. So here you have essentially, if you don't use there that the trace of the action is the Laplacian.
Okay.
Yeah, there in the last identity you have something, at least formally saying that the Laplacian is so if I wonder if this can be used to, so also in the collapse case, to say that to say that the Laplacian is the trace of the action plus something else.
Okay.
Related to the gradient of this. I think that also this also was appears as a conjecture maybe in a paper of Honda. I think this.
Okay, there is this paper with the series of conjectures. So
yes, I think that there is this conjecture about the Witten Laplacian. I wonder if these tools can be used in any way to.
I don't know. Honda tells us something about this in the paper in the compact case, but you require the regularity of the weight. So okay. I don't know, but on the other end, if you want to have a result, a gradient of the function defining the weight must appear, right? So,
yes, exactly, yes.
So I think that the impression is that if you want to have some result, you want to have some regularity of the weight, because otherwise you wouldn't be able to state the result.
I think you need to assume that there's no way that this, for example, this smoothing of the metric can give in some way some regularity of this weight.
I don't know.
Yeah, okay.
But because
it was a very vague question.
Yeah, you know, I don't know, because maybe on the nose, but
okay.
I don't know.
Okay. Okay, thank you.
Grazie.
Are there any other questions? Okay, so if not, we can thank Camillo again. And see you at the next seminar.